Our third video for this week focuses on significance testing for our parameter estimates. And instead of going through all of the details about each parameter estimate and the standard error, I'd rather give you an overview of what standard error represents, where we find it, and how we deal with it. So first, I want to go to the output of a linear model so that you can see what we've covered so far. Remember that we talked about what the meaning of B was, and B is a partial correlation coefficient. In order for us to do hypothesis testing to determine whether B, in this case our partial regression coefficients, are significantly different from 0, what we do is we take our parameter estimate here, we divide it by our estimated standard error, and then that gives us a t-value. And that t-value, then we calculate the p-value associated with the t. And I'll walk you through each one of these steps. But right now, what we're interested in is calculating these standard errors. These standard errors enable us to do the hypothesis testing. So the first thing I want to do is I want to talk to you about the equation. Remember, there are all sorts of equations in the book. I do not want you to memorize them. Instead, I'd prefer that you understand what they are telling you. So a standard error, or the standard error of an unstandardized regression coefficient, in this case a partial correlation coefficient, is a function of a ratio of the standard deviations of y over x. Why? Because it's rise over run. Remember that all slopes are always expressed in terms of y units over x units. Okay, so this is just generic. This is y, standard deviation of y divided by standard deviation x. And then we multiply it by the square root of the variance inflation factor times the square root of, and here's the big thing, this is the amount of variance that is not accounted for. So this is where we are leaving good variance of our dependent variable on the table. We are not accounting for 1 minus r squared of y. And this tells us the residual variance that's left over after our model. The greater this is, the greater our standard error. The greater our variance inflation factor, the greater our standard error. Okay? If there is more variability in y compared to variability in x, the standard errors are larger. So ideally, it would be nice to have even variance in both our criterion as well as our predictor. It's ideal to have low multicollinearity or small VIF, and it's also important to have a large r squared. The more variance that we account for in our model, the smaller our standard errors are of our regression parameters. But then we take 1 minus r squared, okay, the amount of variance that we didn't account for in our model, and we divide it by n minus k minus 1. So what is that telling us? Large samples decrease standard errors. But for every predictor, we take away from our sample size. And then we take away 1 because 1 allows us to calculate the degrees of freedom and therefore generalize our standard errors beyond just our sample. So n, large n, small standard errors. But complex models increase the standard errors. Okay? Now, if we calculate the standard error, I just wrote a very quick way of calculating standard errors, and here you can see from my R code I calculate the standard error. This is just for B1 of x1, so it's 0.1004, and that's right here. Okay, so and we can get that if I already run that summary. Okay, we can do the same thing if it were beta. I don't have the output necessarily for beta, but you can calculate the same standard error for B and for beta. The only thing is we drop this part right here, And the reason why we drop this part is the standard deviation of y equals the standard deviation of x, right? Because they're standardized. All the variables are standardized. Now, how does this relate to t? Well, what we do is we calculate t by taking the coefficient and we divide by our standard error. So I have my coefficient, that's this one right here, 0.6390, and I divide by 0.1004. And what does that give me? 6.36, right? This number is the same as this number. And then when I calculate the probability associated with that t-value, I get something slightly different, and I'm not sure why. Okay. There's probably an error someplace in my calculation. But it's close. 6.45, and I got 6.09 times 10 to the minus 9th. There's an error someplace here. It might be just something that I did. But nevertheless, well, maybe not. Let's see. 6.45. Calculate that. Yeah, it's off. I'll fix this beforehand. But this calculation is the same. It's just calculating the probability associated with that t-value. I might be off with something. So, in summary, what I was able to do was to take, we've already calculated this. I've calculated now the standard error. If I take the estimate and divide by the standard error, I get the t-value. That t-value is then, if we calculate the probability associated with that t, that will result in our p-value. And the p-value, we look for whether it's significantly different from 0 is the null hypothesis, and we're just looking for the probability of observing our parameter estimate given the null model is very small. And all we're looking at is whether it's below 0.05. Next thing is I want to calculate an f, and the f value that I get is pretty simple. There are lots of ways to calculate f. I'm just doing it this way. Cohen and Cohen have different formulas for it, and you can see that my f is 52.57, and I get that right here. I didn't round it. 52.58, right? And then the p-value is 3.33 times 10 to the minus 16th. Again, I'm off with my p-values because there's probably a way that I'm not rounding, or I'm not calculating the actual probability of using a two-tailed test. But nevertheless, it's pretty much the same thing. I'll look into that before class and fix any of the calculations. So you get the idea. The standard errors are calculated so that we can assess how whether our parameter estimates are significantly different from 0, and our f statistic right here gives us an omnibus test, whether our total regression formula significantly predicts our outcome. And the f is an omnibus test. It's related largely to r-squared and to sample size and to model complexity. So from this point forward, we're going to shift over to multicollinearity, and then we're going to talk a little bit more about partial and semi-partial correlations, which will lead us to stepwise and hierarchical regression. So stay tuned for more of that.